fixed function, programmable shaders, and unified shaders. Early graphics hardware used a fixed-function pipeline. The stages were predetermined in silicon, transform and lighting, triangle setup, texturing, rasterization, and blending. Developers could only toggle settings and feed parameters. The hardware applied the same limited sequence to every vertex and every pixel. You could not insert your own math for lighting models, skinning, or post-processing. This made the pipeline fast for its narrow set of tasks, but inflexible. Any effect outside those built-in steps required awkward workarounds, extra passes, or was simply not possible. The next step was the programmable shader pipeline. Hardware vendors added tiny programs that run on the card itself. A vertex shader program runs once per vertex to transform positions, bend or skin characters, compute per vertex lighting, and pass custom values to later stages. A pixel fragment shader program runs for each covered pixel to compute its final color, using your own lighting equation, texture sampling plan, or post-processing effect. These programs are written in high-level shading languages and compiled to run on the card. The result is huge flexibility. Normal mapping, parallax mapping, soft particles, tone mapping, bloom, and many other effects became practical because developers could express the math directly on the hardware. Modern designs then moved to a unified shader architecture. Instead of separate blocks dedicated to vertex programs and pixel programs, the card provides one large pool of identical arithmetic units that can run any shader stage: vertex, geometry, pixel, compute, and more. A hardware scheduler distributes work to this shared pool, so the card can keep its units busy, whether a scene is heavy on pixel shading, heavy on vertex work, or mixed. This improves efficiency, simplifies load balancing, and makes room for general compute workloads, such as physics, simulation, image processing, and machine learning kernels. Unified designs are now the baseline across desktop, mobile, and integrated graphics because they let the hardware adapt to whatever mix of shader tasks a frame demands. Immediate mode rendering and tile-based deferred rendering. Immediate mode rendering is the traditional approach used by most desktop graphics cards. The GPU takes each triangle, transforms it, rasterizes it into pixels, runs pixel shaders, applies blending, and writes the result to the frame buffer in memory, immediately as each piece is processed. This is straightforward, but it means that the card often writes a lot of data out to memory and then reads it back again for later blending, depth testing, or post-processing. Because external memory access is expensive in both time and power, this approach requires very high memory bandwidth, which is why desktop graphics cards are paired with wide GDDR or HBM memory buses. Tile-based deferred rendering works differently. Instead of sending every pixel directly to the frame buffer right away, the GPU first breaks the screen into small tiles. Each tile holds a portion of the geometry and pixel data. The GPU sorts which primitives affect each tile, then runs shading for all of the pixels in that tile at once, using fast on-chip memory buffers instead of writing every intermediate step out to external memory. Only the finished tile is written back to the frame buffer. This approach saves bandwidth and reduces power usage because external memory is accessed much less often. It is especially well suited to mobile and integrated GPUs, where power efficiency is critical. The trade-off is complexity. A tile-based design needs to store and sort geometry before shading, which adds overhead for very complex scenes with many overlapping objects. Immediate mode rendering, while less efficient in bandwidth, is simpler and more predictable for large-scale PC and console games with massive geometry. Because of this, desktop GPUs from Nvidia and AMD traditionally use immediate mode, while mobile GPUs from ARM, Imagination, and Apple rely heavily on tile-based deferred rendering. Nvidia Tesla architecture. Nvidia's G80 introduced the company's first unified shader design for consumer graphics, launching with the GeForce 8800 series on November 8, 2006, and adding full DirectX 10 and Shader Model 4.0 support. Unified shaders meant one pool of arithmetic units could run any stage, vertex, pixel, or geometry, so the scheduler could keep the chip busy regardless of workload mix. This was a major step beyond the older split pipelines. Inside the chip, the Tesla design arranged 128 scalar cores into 16 streaming multiprocessors, grouped into 8 texture processor clusters. This layout scaled well and fed the unified shader model efficiently for both graphics and general computation. G80 also arrived arrived alongside CUDA, Nvidia's general-purpose programming model, turning the graphics processor into a parallel compute device for simulation and scientific tasks, planting the seeds for modern GPU computing across GeForce, Quadro, and data center products. Nvidia Fermi and Kepler. Fermi, 2010, Fermi brought full DirectX 11 features and a much wider, more general-purpose design. Each streaming multiprocessor added larger caches, more load store units, and many more arithmetic lanes, so complex shaders and compute kernels ran faster. Geometry stages were strengthened to push more tessellation, and raster and blending blocks were expanded for higher fill rate. Fermi also improved context switching and error protection to make general computing on the graphics card more reliable. These changes made the graphics card better at both games and parallel computing. Kepler, 2012, Kepler focused on efficiency per watt and higher throughput. The new SMX multiprocessor grouped more arithmetic units under a simpler scheduler, raising delivered performance while lowering power versus Fermi at the same manufacturing process. For computing, Kepler introduced dynamic parallelism. Kernels can launch new kernels on the device, and Hyper-Q, which lets many CPU threads feed the same graphics card to keep it busy. In games, this translated into more performance per square millimeter and cooler, quieter boards. Nvidia Maxwell and Pascal. Maxwell, 2014 to 2015, Maxwell redesigned the streaming multiprocessor into the SMM unit to deliver much higher efficiency per watt than Kepler. The changes included leaner control logic, finer-grained clock gating, improved instruction scheduling, and better load balancing, so more of the silicon's math units stayed busy while using less power. Maxwell also expanded the L2 cache and improved memory compression, which cut external memory traffic and raised effective bandwidth, critical for gaming performance without wider memory buses. Cards like GeForce GTX 980 and 970 showcased these gains. For compute, Maxwell continued full CUDA support while prioritizing gaming efficiency. Pascal, 2016 to 2017, Pascal moved to 16-nanometer FinFET manufacturing and pushed both graphics and compute forward. The data center Tesla P100 combined HBM2 memory, NVLink high-bandwidth interconnect, and unified memory with page migration, making very large datasets easier to program and faster to move between the central processor and the graphics processor. On gaming cards like GeForce GTX 1080, Pascal paired GDDR5X with new graphics features such as simultaneous multi-projection for efficient multi-display and virtual reality rendering, plus finer preemption, so long compute or graphics tasks could be interrupted more gracefully. Overall, Pascal delivered higher performance, much better performance per watt, and a major uplift in memory bandwidth versus Maxwell. Nvidia Turing, Ampere, ADA, and Blackwell. Turing, 2018, introduced two new fixed units alongside the programmable shaders, ray tracing cores that accelerate bounding volume hierarchy traversal and triangle ray tests, and tensor cores that accelerate matrix math for artificial intelligence. This enabled hybrid rendering, rasterization for primary visibility, plus hardware-accelerated ray tracing for reflections, global illumination, and shadows, denoised by artificial intelligence filters. Turing also added advanced shading features such as mesh and task shading in the professional stack, variable rate shading, and a modern cache hierarchy to feed the cores efficiently. Ampere, 2020, increased throughput per watt and advanced the artificial intelligence path. Third-generation tensor cores added new math formats such as TensorFloat 32 and BrainFloat 16, giving speedups for training and inference without code changes. Graphics chips like GA102, used in the GeForce RTX 3880 family, paired wider data paths with faster memory and better compression, raising effective bandwidth for ray-traced and rasterized scenes. The result was higher frame rates at the same power and faster artificial intelligence denoising and super resolution. Ada Lovelace, 2022. Ada redesigned the front-end and scheduling for ray-traced workloads. Shader execution reordering dynamically groups similar rays so the hardware runs more coherent code paths, significantly boosting ray-tracing performance in complex scenes. Fourth-generation tensor cores, plus a new optical flow accelerator, enabled deep learning supersampling 3-frame generation, which synthesizes intermediate frames to increase perceived frame rate. Ada also expanded ray-tracing core capability and improved improved the memory subsystem to keep the arithmetic units busy. Blackwell, 2024 to 2025, is a next-generation architecture that scales further for artificial intelligence and graphics. In the data center family, Blackwell packages two large dies into a single logical graphics processor, linked by a 10 terabytes per second on-package interconnect, and raises transistor counts dramatically on a custom 4-nanometer process. On the consumer side, GeForce RTX 50 series cards bring Blackwell features to games, including the next wave of ray tracing and artificial intelligence acceleration and deep learning supersampling 4 with multi-frame generation. Professional RTX Pro Blackwell cards add very large frame buffers, next-generation GDDR7 memory interfaces, and updated ray tracing and tensor engines for creation and simulation. ATI and AMD Terascale. Terascale was ATI's and later AMD's last major architecture before Graphics Core Next. It used very long instruction word-style shader cores. In very long instruction word, each instruction packs several independent operations that must all be executed in the same cycle. Early Terascale parts used 5-way, very long instruction word groups. If a shader program did not have 5 perfectly independent operations ready at once, some lanes sat idle. That made peak numbers look high, but real programs often left performance on the table due to underutilization. Later, AMD introduced Terascale 3 with 4-way, very long instruction word groups instead of 5. Reducing the width made it easier for compilers to keep the lanes busy, improving real throughput at the same clock speed. Terascale 3, used in many Radeon HD 6000 models, also strengthened fixed-function geometry, adding a more capable tessellation unit to improve DirectX 11 workloads. Across the Terascale generations, AMD delivered full DirectX 11 feature support on the Radeon HD 5000 family and continued it on Radeon HD 6000. Terascale could run general compute via OpenCL, but the very long instruction word style and scheduling constraints made wide compute use harder than on later designs. Those limitations are a key reason AMD moved to Graphics Core Next afterward, which replaced very long instruction word with a more flexible scalar plus single instruction, multiple data approach. AMD RDNA 1, RDNA 2, RDNA 3, and RDNA 4. RDNA 1. The first Radeon DNA architecture replaced Graphics Core Next with a gaming-focused design. It introduced the workgroup processor layout, streamlined caches, and a shorter graphics pipeline for better performance per watt compared with Vega-era designs. Cards like Radeon RX 5700 used this first generation. Background and lineage to later RDNA generations documented in AMD and third-party overviews. RDNA 2 second-generation RDNA added full DirectX 12 Ultimate feature support, including hardware-accelerated ray tracing, mesh shading, variable rate shading, and sampler feedback. It also debuted Infinity Cache, a large on-die cache that reduces external memory traffic and boosts effective bandwidth. RDNA 2 powered Radeon RX 6000 and the current game consoles from Microsoft and Sony. RDNA 3 third-generation RDNA introduced a chiplet design on desktop cards with separate graphics compute and memory cache dies, plus updated compute units and second-generation Infinity Cache. It launched in the Radeon RX 7000 family and later appeared in several handheld and console refresh products. RDNA 4 fourth-generation RDNA arrived as the Radeon RX 9000 series, adding improved ray tracing accelerators and expanded artificial intelligence acceleration, alongside new upscaling features branded Fidelity FX Super Resolution 4 on supported games and drivers. Public launches and driver notes place RX 9000 parts and FSR4 in early 2025 and later driver updates. Intel. Before discrete ARC cards, Intel shipped many generations of integrated graphics in its laptop and desktop processors. These designs evolved from fixed function blocks into fully programmable unified shaders. The XELP step, introduced with the Tiger Lake processors, was a major rewrite focused on efficiency. More execution units per slice, larger caches, improved media engines, and modern features like variable rate shading. It kept power low for laptops while raising real gaming performance compared with earlier Intel integrated graphics. XELP is the foundation that later discrete designs build on. Intel's first modern discrete gaming cards used the XeHPG architecture branded Arc Alchemist. Key additions were hardware ray tracing units per shader array for bounding volume traversal and ray triangle tests, matrix engines, called XMX, for artificial intelligence workloads such as super resolution in Xe supersampling, full DirectX 12 ultimate feature support, including mesh shading and sampler feedback. Alchemist established Intel's driver model and toolchain for desktop gaming and for compute via one API. The second-generation Arc chips, marketed as the B series, improved front-end throughput, caches, and the ray tracing blocks, and delivered faster mesh shading and broader game compatibility. Intel announced the B580 and B570 in December 2024, with retail availability starting mid-December and January. Intel highlights higher performance per watt and better scheduling and compression versus Alchemist. Celestial is the third-generation step on Intel's public graphics roadmap after Battlemage. As of September 22, 2025, Intel has discussed Celestial as a future architecture, but has not provided retail launch details comparable to Alchemist or Battlemage. Treat it as the next planned evolution of the same unified shader design, expected to advance ray tracing, machine learning acceleration, and scheduling. Status based on Intel's public overviews to developers. AM286, AM386, and AM486. AMD entered the x86 market by building Intel-compatible central processing units for personal computers. The AM286 arrived in the mid-1980s as a software-compatible version of the Intel 80286. It executed the same x86 instruction set, so programs written for the personal computer ecosystem ran without changes. The important technical feature of this generation was protected mode, which allowed the processor to address much larger amounts of memory and to isolate programs from each other for stability. In practice, most consumer systems still booted in real mode for older software, but the AM286 established AMD as a reliable second source for central processing units and helped reduce system prices through competition. The AM386 moved AMD into true leadership in the early 1990s. Architecturally, the 386 family introduced a full 32-bit design with 32-bit registers, a 32-bit data path, and a 32-bit address space, which dramatically expanded what operating systems could do. Hardware paging enabled virtual memory, letting computers use disk space to extend usable memory. For buyers, AMD's AM386 parts were known for strong clock speeds for the time and aggressive pricing, which accelerated the adoption of 32-bit operating systems such as early Microsoft Windows NT and advanced versions of Microsoft Windows and Unix-like systems. Software compatibility with the existing x86 stack remained intact, so businesses could move forward without rewriting applications. The AM486 refined the same instruction set and brought higher per-clock performance through deeper pipelining and an on-chip Level 1 cache, which reduced trips to slower main memory. Many AM486 models also integrated a floating-point unit in the DX variants, improving performance in mathematics-heavy tasks such as computer-aided design and early three-dimensional graphics. Write-back cache policies and clock doubling or clock tripling models, commonly labeled DX2 and DX4, delivered major speed gains while staying on affordable motherboards. In the marketplace, the AM486 cemented AMD's reputation for delivering comparable performance to Intel at lower prices, setting the stage for AMD's first fully in-house designs that followed. K5. The AMD K5, released in 1996, was the company's first fully in-house x86 microarchitecture. Unlike the AM386 and AM486, which were reverse-engineered Intel-compatible chips, the K5 was designed completely by AMD engineers. The goal was to compete directly with Intel's Pentium. Architecturally, the K5 translated the traditional x86 complex instruction set into smaller, simpler microoperations internally, a design inspired inspired by RISC principles. This approach should have improved efficiency, but the K5 suffered from long pipelines and design complexity that limited its clock speeds. While it could execute Pentium-class instructions, the K5 was often late to market and slower in real-world applications. Limited yields and difficulty scaling to higher frequencies meant it struggled to gain wide adoption. Despite its shortcomings, the K5 was historically important as AMD's first attempt at original CPU design, proving the company could engineer its own processor architecture rather than just cloning Intel's K6 series. In 1997, AMD acquired a company called NextGen, and much of NextGen's engineering work went into the design of the K6 series. The AMD K6 processors arrived as credible competitors to Intel's Pentium and Pentium II. They offered full support for the MMX multimedia instruction set, strong integer performance, and could fit into existing Socket 7 motherboards, which made them attractive for upgrades. The K6-2 in 1998 was especially popular because it introduced AMD's 3D Now instruction set, aimed at accelerating three-dimensional graphics in an era before dedicated graphics cards were powerful. The K6-3 followed with an integrated Level 2 cache, boosting performance further. For budget-conscious buyers, the K6 line delivered excellent value and helped AMD gain wider recognition in the consumer market. This period was critical in establishing AMD as a serious competitor rather than just a second-source supplier. K7 Athlon. The Athlon, launched in 1999 under the K7 architecture, was AMD's true breakthrough into high-performance computing. Built for the new Slot A interface, the Athlon introduced a completely new microarchitecture with a high-speed double data rate front-side bus licensed from Digital Equipment Corporation's Alpha processors. It included 3 fully pipelined floating-point units, giving it excellent performance in scientific and graphics workloads. The Athlon quickly became the first consumer central processing unit to break the 1 GHz clock speed barrier in the year 2000, a milestone that Intel had been racing toward with the Pentium III. Performance benchmarks showed the Athlon beating or matching Intel's best chips of the era in both integer and floating-point tasks. With competitive performance and aggressive pricing, the Athlon K7 gave AMD its first real chance to lead the processor market. K8. In 2003, AMD introduced the K8 architecture, which powered the Athlon 64 for consumers and the Opteron for servers. This generation was revolutionary for several reasons. First, AMD added native support for 64-bit x86 instructions, later called x86-64 or AMD 64, extending the traditional 32-bit instruction set to handle vastly larger memory spaces. Second, AMD integrated the memory controller directly onto the processor die, eliminating the bottleneck of the Northbridge chip and reducing memory latency. Third, AMD created Hypertransport, a high-speed interconnect that replaced the front-side bus for communication between the processor, chipset, and other components. These innovations gave the Athlon 64 and Opteron strong performance advantages over Intel's Pentium IV, especially in multiprocessor and memory-intensive workloads. For several years, AMD enjoyed clear technical leadership, and the K8 architecture laid the foundation for all future x86-64 computing. K10. AMD released the K10 architecture in 2007 with the Phenom brand for desktops and Barcelona for servers. The most important feature was the introduction of true native quad-core designs, meaning all 4 cores were on a single piece of silicon rather than multiple dual-core dies packaged together. This improved communication between cores and reduced latency compared to Intel's multi-chip modules at the time. The K10 also featured an improved memory controller, Hypertransport 3.0 for faster interconnect speeds, and a larger shared level 3 cache. However, early Phenoms were affected by a hardware bug known as the TLB bug, which forced a BIOS workaround that reduced performance. Even after fixes and later models like the Phenom 2, AMD struggled because Intel's Core 2 Duo and Core 2 Quad processors delivered much higher instructions per clock and higher clock speeds. While K10 showed AMD's ability to innovate with native quad-core designs, it was overshadowed in the marketplace and marked the beginning of a difficult period for the company. Bulldozer family. In 2011, AMD launched the Bulldozer architecture, which powered the FX series of processors. Bulldozer introduced a new design concept called modules. Each module contained 2 integer cores that shared some resources, such as the floating point unit and instruction fetch. AMD marketed these modules as multiple cores, which gave the FX processors very high advertised core counts, up to 8 cores in mainstream models. In practice, however, the shared resources meant per-core performance was much weaker than Intel's Sandy Bridge and later Core I-series processors. The long pipelines and design trade-offs led to poor instructions per clock, high power consumption, and underwhelming gaming performance. Later iterations such as Piledriver, Steamroller, and Excavator tried to refine the design but never fully closed the gap. While the Bulldozer family looked impressive on paper with high clock speeds and many cores, in reality it damaged AMD's reputation and left Intel with a near monopoly on high-performance desktop CPUs through most of the 2010s. Zen 1. In 2017, AMD made a major comeback with the launch of the Zen architecture under the Ryzen brand. Built on a 14-nanometer process, Zen processors offered up to 8 cores and 16 threads for mainstream desktop users, something Intel was not offering at the time. Zen introduced simultaneous multi-threading, AMD's version of Intel's hyper-threading, which allowed each core to handle 2 threads. The new architecture provided a dramatic improvement in instructions per clock compared to Bulldozer, often more than 50% higher. The Ryzen 7 1800X became the flagship of the Ryzen 1000 series, delivering workstation-level performance to consumer desktops. Ryzen also reintroduced AMD as a serious competitor in both gaming and productivity workloads, and the long-lived AM4 socket gave buyers confidence that their motherboards would support multiple generations of upgrades. Zen Plus. In 2018, AMD refined the Zen design into Zen Plus, produced on a 12-nanometer process. While it was not a complete architectural overhaul, Zen Plus brought lower cache and memory latencies, slightly higher clock speeds, and improved efficiency. The Precision Boost 2 and XFR2 features allowed processors to dynamically adjust their frequencies more intelligently based on workload and cooling, resulting in better real-world performance. The Ryzen 2000 series, led by chips such as the Ryzen 7270X, closed the gap with Intel in gaming while continuing to dominate in multi-threaded productivity thanks to high core counts at affordable prices. Zen Plus demonstrated AMD's ability to refine its designs quickly and deliver consistent generational improvements, keeping momentum going into the next major leap. Zen 2. In 2019, AMD introduced Zen 2, a transformative architecture built on a 7-nanometer process by TSMC. Zen 2 debuted the chiplet design, where multiple small processor dies called core complexes were connected through a central input-output die. This modular approach reduced manufacturing costs, improved yields, and allowed AMD to scale core counts more easily. Mainstream desktop processors reached up to 16 cores and 32 threads with the Ryzen 9 3950X, far beyond Intel's offerings at the time. Zen 2 also introduced support for PCI Express 4.0, doubling bandwidth for graphics cards and storage devices. Performance per clock improved significantly, making Zen 2 processors competitive in both single-threaded tasks like gaming and heavily multi-threaded workloads such as video editing and software compilation. The combination of efficiency, scalability, and features gave AMD a massive advantage in value and performance, marking a turning point in the CPU market. Zen 3. Launched in late 2020, Zen 3 refined the chiplet design and made major architectural changes. The biggest improvement came from unifying the core complex. Up to 8 cores now shared a single large Level 3 cache, reducing latency and boosting gaming performance. Instructions per clock improved by around 19%. Compared to Zen 2, which finally allowed AMD to surpass Intel in both gaming and productivity. The flagship Ryzen 9 5950X offered 16 cores and 32 threads, while even mid-range processors like the Ryzen 5560X became some of the best-selling CPUs for gamers. Zen 3 was widely praised as one of the strongest CPU launches in AMD's history, firmly re-establishing the company as a leader in both innovation and market share. Zen 4. In 2022, AMD released the Zen 4 architecture, moving to the new AM5 socket after years of supporting AM4. Zen 4 processors were manufactured on TSMC's 5nm process, allowing higher clock speeds and better energy efficiency. They introduced support for DDR5 memory and PCI Express 5.0, giving access to the latest high-speed storage and graphics technologies. The architecture also expanded instructions per clock, improved branch prediction, and enhanced integrated graphics by adding RDNA 2-based graphics cores on most models. Ryzen 7000 chips reached boost frequencies above 5.5 GHz, making them some of the fastest consumer processors available. However, the platform required new motherboards and DDR5 memory, which increased upgrade costs for buyers. Despite this, Zen 4 maintained AMD's lead in multi-core performance and positioned the company well for future growth. Zen 5. In 2024, AMD introduced Zen 5, its most advanced architecture yet. Built on a refined 4nm process with redesigned front-end and execution pipelines, Zen 5 focused on further improving efficiency and instructions per clock. A key emphasis was on accelerating artificial intelligence and machine learning tasks with new instructions and optimized scheduling. The Ryzen 9000 series delivered higher performance at lower power, continuing AMD's chiplet strategy with improved interconnect bandwidth. Early models such as the Ryzen 99950X pushed multi-core performance even further while maintaining strong single-threaded efficiency for gaming. With Zen 5, AMD strengthened its competitive position against Intel's latest architectures and signaled a long-term commitment to advancing both consumer and professional computing. Von Neumann architecture. The von Neumann architecture is the earliest and most influential CPU design model, proposed in the mid-1940s. It is built around the idea of a single memory space that stores both instructions and data. This means that program code and the values the code operates on are kept in the same memory and accessed through the same data pathways. The system is composed of 4 key components: the central processing unit, CPU, the memory unit, the input-output system, and the control unit. Inside the CPU, the arithmetic logic unit, ALU, performs mathematical and logical operations, while the control unit fetches instructions from memory, decodes them, and coordinates their execution. A major characteristic of this design is the fetch-decode-execute cycle. The CPU fetches an instruction from memory, decodes what operation it represents, and then executes it. After that, it moves to the next instruction. Because instructions and data share the same bus, only one operation can occur at a time, either fetching an instruction or transferring data. This creates the von Neumann bottleneck. The shared memory bus limits how much data and how many instructions can move between the CPU and memory at once. As CPUs became faster, this bottleneck became a major performance limitation, since the processor often had to wait for instructions or data to arrive from memory. Despite this limitation, the von Neumann model became the foundation for most general-purpose computers, and even modern processors still reflect this structure at a basic level. Harvard architecture. The Harvard architecture was developed as an alternative to the von Neumann model. Its defining feature is the use of separate memory spaces for instructions and data. This means program code is stored in one memory system, while data is stored in another. Each memory has its own dedicated bus for transfers. Because of this separation, the CPU can fetch an instruction and access data at the same time. This parallelism removes the bottleneck of von Neumann systems, where instruction and data transfers compete on the same bus. Harvard systems are therefore capable of higher throughput, especially in specialized computing tasks. The architecture is common in embedded systems, microcontrollers, and digital signal processors, DSPs, where predictable performance and efficiency are more important than general-purpose flexibility. For example, many microcontrollers used in appliances, cars, and industrial machines rely on a Harvard-style design because it allows instructions to be fetched consistently while data operations happen simultaneously. Modern CPUs sometimes use a modified Harvard architecture, where the distinction between instruction and data storage is blurred. For example, a CPU may keep instructions and data in separate caches for speed, but ultimately store both in the same main memory. This allows the processor to take advantage of Harvard-style parallelism in the short term, while still being compatible with the unified memory of general-purpose systems. CISC, Complex Instruction Set Computer. CISC stands for Complex Instruction Set Computer. It describes a CPU design design philosophy where the processor is equipped with a large set of instructions, some of which can perform multi-step operations in a single command. For example, a CISC instruction might load data from memory, perform a calculation, and store the result back in memory, all with one instruction. The idea behind CISC was to make programming easier and reduce the number of instructions a program needed. In the early days of computing, memory was expensive and compilers were less advanced. By packing more functionality into each instruction, CISC allowed smaller, more compact programs that ran efficiently on limited hardware. CISC processors rely heavily on microcode, which translates these complex instructions into smaller internal steps that the CPU can execute. This makes the hardware more complicated, but it simplifies software development and helps programs run with fewer lines of code. The most well-known CISC architecture is x86, originally developed by Intel in the late 1970s. x86 became the dominant standard for desktop and laptop computers. It is still in widespread use today, powering most Windows PCs and many servers. Over time, x86 processors have grown extremely sophisticated, with features like instruction pipelining, superscalar execution, and out-of-order processing layered on top of the original CISC foundation. One trade-off of CISC is that the complexity of instructions can slow down execution. Since not all instructions are used equally, the CPU must handle many cases, making the design more intricate. However, advances in chip manufacturing and caching techniques have kept CISC architectures competitive for decades. RISC, Reduced Instruction Set Computer. RISC stands for Reduced Instruction Set Computer. It takes the opposite approach of CISC by using a small, highly optimized set of instructions. Each instruction is designed to execute in a single clock cycle whenever possible. Instead of performing multi-step operations in one instruction, RISC CPUs break tasks into simple operations that can be executed quickly and consistently. The philosophy behind RISC is that simpler instructions executed more rapidly can outperform complex instructions that take multiple cycles. Because of this, RISC processors focus on a few key design principles. Load, store, architecture. Only dedicated instructions move data between memory and CPU registers. All other operations work strictly on data already loaded into registers. Uniform instruction length. Instructions are usually the same size in memory, making it easier to fetch and decode them quickly. Pipeline-friendly design. With simple, predictable instructions, RISC processors can use deep instruction pipelines, executing multiple instructions in different stages at once. RISC gained popularity in the 1980s with designs like MIPS, Spark, and ARM. ARM in particular has become the most widespread RISC architecture, dominating smartphones, tablets, and more recently laptops and servers. Its efficiency and low power consumption make it ideal for battery-powered devices. Over time, the line between RISC and CISC has blurred. Modern x86 processors use internal techniques similar to RISC, breaking down complex CISC instructions into simpler micro-operations. Meanwhile, RISC processors have gained more complex instructions for efficiency. Still, the RISC philosophy of simplicity, speed, and efficiency remains central to modern CPU design. EPIC, Explicitly Parallel Instruction Computing. EPIC, or Explicitly Parallel Instruction Computing, is a CPU design model that evolved from VLIW. Like VLIW, it relies on the compiler to identify instructions that can run in parallel. However, EPIC introduces additional features to address some of VLIW's weaknesses, especially the problem of wasted execution slots when the compiler cannot find enough independent instructions. The core idea is that the compiler marks instructions with hints, called explicit parallelism, that tell the CPU which instructions can safely execute at the same time. The processor then groups these instructions into bundles and runs them in parallel, while still maintaining safeguards against hazards like memory dependencies. EPIC also adds advanced features, such as predicated execution. Instead of branching on conditions, many instructions can be executed conditionally, reducing pipeline stalls from branch mispredictions. Speculative loading. The CPU can preload data from memory before it knows if it will be needed, hiding memory latency. Large register files. More registers give compilers greater flexibility in scheduling instructions without relying heavily on memory. The most famous EPIC implementation was Intel Itanium, launched in 2001. It was intended as the future of server and workstation computing, replacing x86 entirely. However, Itanium faced significant challenges. Compilers struggled to generate efficient parallel bundles for general-purpose software. Legacy software compatibility was poor, and x86 processors kept improving faster than expected. Although Itanium and EPIC ultimately failed in the mass market, the ideas influenced later CPU designs. Techniques like predication and speculative execution became common in superscalar architectures, showing how even unsuccessful architectures can shape future processor evolution. Superscalar architecture. Superscalar architecture is a CPU design that allows the processor to execute multiple instructions per clock cycle by using multiple execution units inside the chip. Instead of fetching and running one instruction at a time, a superscalar CPU can fetch several instructions, analyze them, and send them to different units that handle arithmetic, memory access, or logic operations simultaneously. The key challenge is determining which instructions can safely run in parallel. This requires complex hardware mechanisms for instruction scheduling, dependency checking, and hazard detection. If two instructions depend on each other's results, they cannot run at the same time. The CPU must also handle branch instructions, which can disrupt the instruction pipeline if the processor predicts incorrectly which path the program will take. To deal with these challenges, superscalar CPUs use techniques like out-of-order execution. Instructions can be executed as soon as their inputs are ready, rather than strictly in program order. Branch prediction. The CPU guesses which way a branch will go to keep the pipeline full, rolling back if the guess is wrong. Register renaming avoids false dependencies by mapping program variables to different physical registers. Most modern general-purpose processors are superscalar. For example, x86 CPUs from Intel and AMD, as well as ARM-based processors in smartphones, all include multiple execution units that can process several instructions at once. This design has been a major factor in performance scaling since the 1990s. The limitation of superscalar scaling is that as instruction-level parallelism is exploited further, the benefits diminish. Programs often do not have enough independent instructions in sequence to keep many execution units busy, creating a ceiling on efficiency. This is one reason why the industry later shifted focus toward multi-core and parallel computing. Multi-core and many-core CPUs. A multi-core CPU places multiple independent processing units, called cores, onto a single chip. Each core can execute its own sequence of instructions, allowing several tasks to run in parallel. For example, a quad-core processor can run 4 threads at once, improving multitasking and speeding up software that is written to take advantage of parallel execution. The motivation for multi-core designs came from the mid-2000s, when increasing clock speeds became impractical due to power consumption and heat. Instead of making one core faster, manufacturers began adding more cores to improve performance through parallelism. This shift marked a major change in CPU development. Many core CPUs extend the idea further, integrating dozens or even hundreds of cores. These are designed for highly parallel workloads like scientific simulations, financial modeling, and artificial intelligence. Many core processors are often found in supercomputers and high-performance computing HPC systems. However, more cores only improve performance if software is designed to use them. Writing parallel programs is much more complex than writing single-threaded code, since tasks must be divided into independent parts that can run without interfering with each other. If the workload cannot be parallelized, extra cores provide little benefit. Modern desktop and server CPUs typically combine multiple cores with other techniques, such as simultaneous multithreading, SMT, where each core runs more than one thread at once. This maximizes core utilization when some threads are waiting for data. Today's consumer processors often have between 4 and 16 cores, while server and HPC processors can reach 64 cores or more. Many core GPUs, with thousands of simpler cores, represent another path to massive parallelism for highly specialized workloads. Hybrid architectures. Hybrid CPU architectures combine different types of cores on the same chip, each optimized for different workloads. The most common model is ARM's big dot little design. In this setup, big cores are powerful and optimized for performance, while little cores are smaller, more energy efficient, and handle lighter tasks. The operating system dynamically switches between cores depending on the workload. For example, browsing the web or checking email might run on little cores to save battery, while gaming or video editing activates the big cores for maximum performance. Apple's M-series processors use a similar approach, pairing performance cores with efficiency cores. Their unified memory system and advanced power management allow macOS to distribute tasks intelligently, giving long battery life while still delivering high performance when needed. This hybrid model has been one of the reasons Apple Silicon chips significantly outperform many traditional x86 laptop CPUs in both performance and energy efficiency. Hybrid architectures are not limited to phones and laptops. Even in servers, chip makers experiment with mixing different types of cores or combining CPUs with specialized accelerators. For example, some processors integrate AI accelerators, GPUs, or DSP units alongside general-purpose cores. This allows them to handle diverse workloads more efficiently than a single core type could. The strength of hybrid architectures lies in their flexibility. Instead of designing one core type to do everything, manufacturers assign different tasks to cores best suited for them. This approach improves both performance and energy efficiency, making hybrid CPUs a key trend in modern processor design. The one on screen? Worth a look if you like knowing what most people don't.